Everything you think you know about the beginning of the universe is wrong, and by the time you finish reading this, you will never think about the word nothing the same way again. The universe did not come from nothing. That single sentence might sound like a throwaway claim, but it carries the weight of over a century of physics, mathematics, and philosophy. You have probably heard the popular catchphrase dozens of times: the universe began from nothing. It rolls off the tongue easily, almost poetically, and it has been repeated so often in documentaries, best-selling books, and late-night conversations that most people accept it as settled science. But it is not. The phrase is, at best, a gross oversimplification and, at worst, a deeply misleading myth. The real story behind how the universe came to exist is far stranger, far richer, and far more humbling than the idea that some cosmic switch flipped in a void of absolute emptiness and bang, everything appeared. To understand why, we need to dismantle several layers of misunderstanding, starting with the most famous two words in all of cosmology: the Big Bang. Say those words, and almost everyone on the planet conjures the same mental image: an explosion, a blinding flash of light ripping through a dark and empty void, matter flying outward from a single point like shrapnel from a detonated bomb. It is vivid, dramatic, and almost entirely incorrect. The Big Bang Theory, as it actually exists in physics, does not describe an explosion in the conventional sense. It does not describe matter being flung through pre-existing space the way fragments scatter from a firecracker. And it certainly does not claim that the universe sprang from some absolute state of nothingness. What the Big Bang Theory actually says is far more subtle. It says that the observable universe was once in an extraordinarily hot, extraordinarily dense state, and that it has been expanding and cooling ever since. That is it. The theory is a description of how the universe evolved from an early condition, not a description of how that condition came to be. There is a profound difference between explaining what happened after a certain moment and explaining why that moment existed in the first place. And the Big Bang Theory concerns itself only with the former. To make this concrete, consider one of the most commonly used analogies in cosmology: the surface of a balloon. Imagine drawing small dots all over an uninflated balloon with a marker. Each dot represents a galaxy. Now inflate the balloon. As the rubber stretches, every single dot moves away from every other dot. No dot is at the center of the expansion. The expansion is happening everywhere on the surface, simultaneously. This is what the expansion of space looks like. The galaxies are not flying away from some central detonation point in the way that debris flies from a bomb. Instead, the fabric of space itself is stretching, and as it stretches, the distances between galaxies grow. There is no center to this expansion. There is no edge. The expansion is a property of space itself, and it is happening everywhere all at once. The observational evidence for this stretching of space is among the most robust in all of science. In 1929, the American astronomer Edwin Hubble published data showing that distant galaxies are moving away from us, and that the farther away a galaxy is, the faster it recedes. This relationship, now called the Hubble-Lemaitre law, was the first direct evidence that the universe is expanding. The velocity at which a galaxy recedes is proportional to its distance. A galaxy twice as far away moves twice as fast. This pattern is exactly what you would expect if space itself were uniformly stretching, carrying galaxies along with it like raisins in a rising loaf of bread. Then in 1964, two American radio astronomers named Arno Penzias and Robert Wilson, working at Bell Labs in Holmdel, New Jersey, stumbled upon what would become one of the most important discoveries in the history of science. While calibrating a large horn antenna designed for satellite communications, they detected a persistent background hiss of microwave radiation coming from every direction in the sky. No matter where they pointed the antenna, north, south, east, west, up, down, the signal was there, uniform and omnipresent. They could not eliminate it. They even cleaned pigeon droppings off the antenna, thinking the birds might be the source. They were not. What Penzias and Wilson had accidentally discovered was the cosmic microwave background radiation, or CMB, the faint afterglow of the hot, dense state of the early universe. This radiation was released roughly 380 0.000 years after the initial expansion began. At the moment when the universe had cooled enough for atoms to form and for light to travel freely through space for the first time. That light has been traveling ever since, stretching with the expansion of space. Its wavelength redshifting from the visible spectrum down into the microwave range. Today it fills the entire sky with a nearly uniform temperature of about 2.725 degrees above absolute zero. The CMB is essentially a baby photograph of the universe. A snapshot of what things looked like when the cosmos was less than 400,000 years old. And it matches the predictions of the Big Bang model with breathtaking precision. Penzias and Wilson received the Nobel Prize in Physics in 1978 for their discovery, and subsequent missions, most notably NASA's COBE, WMAP, and the European Space Agency's Planck satellite, have mapped the CMB in exquisite detail, revealing tiny temperature fluctuations on the order of 1 part in 100,000 that correspond to the seeds of all the structure we see in the universe today: galaxies, galaxy clusters, superclusters, and the vast cosmic web. All of this evidence, the recession of galaxies, the cosmic microwave background, the abundances of light elements like hydrogen and helium that were forged in the first few minutes of expansion, points unambiguously to the conclusion that the universe was once much hotter and much denser than it is now. But none of it tells us what came before that hot, dense state. None of it tells us why that state existed. And none of it tells us that the universe emerged from nothing. Now here is something that most people do not know. The very name Big Bang was coined as an insult. The term was invented by the British astronomer Fred Hoyle during a BBC radio broadcast on March 28, 1949. Hoyle was a proponent of the rival steady-state theory, which held that the universe had no beginning and no end, that it had always existed in roughly the same form. He found the idea of a sudden beginning absurd, and during his BBC appearance he dismissively described the competing theory as claiming the universe started in a Big Bang. The name was intended as mockery. It stuck anyway. It stuck so well, in fact, that it became the universally recognized label for the theory Hoyle despised. The irony runs even deeper when you consider the man who actually developed the theoretical framework. The Belgian physicist and Catholic priest Georges Lemaitre was the first to propose, in 1927, that the universe is expanding, and in 1931 he took the idea further, suggesting that if you rewind the expansion far enough, you arrive at what he called the primeval atom, a single, unimaginably dense point from which everything emerged. Lemaitre was careful to keep his science and his theology separate. When Pope Pius XII publicly declared in 1951 that the Big Bang was evidence of divine creation, Lemaitre was reportedly uncomfortable. He advised Vatican officials that the scientific theory should not be conflated with religious doctrine, that science describes how things happen and theology addresses why, and that mixing the two does a disservice to both. His caution was well placed. The Big Bang theory is a scientific model that describes the expansion and cooling of the universe. It is not a creation story. It does not say where the initial hot, dense state came from. It does not say what caused it. And it emphatically does not say that the universe erupted out of nothing. This brings us to one of the most important and most misunderstood concepts in all of modern physics. What does nothing actually mean? In everyday life, the word is simple enough. Nothing means the absence of anything. An empty room, an empty pocket, an empty glass. But in physics, particularly in quantum physics, the word takes on a radically different meaning, or rather, it loses its meaning almost entirely. Let us start with the simplest version of nothing that a physicist might consider. A perfect vacuum. Strip away all matter. Remove every atom, every molecule, every particle of dust. Pump out every photon of light. Cool the space to absolute zero. What are you left with? The intuitive answer is nothing. The correct answer is something far more interesting. According to quantum field theory, the framework that underpins our most successful description of the subatomic world, a vacuum is never truly empty. Even in the most perfect vacuum imaginable, even at the lowest possible temperature, the quantum fields that permeate all of space never fully settle down. They fluctuate. They jitter. They buzz with a restless, irrepressible energy called zero-point energy. This is not a metaphor. It is not a poetic flourish. It is a measurable empirical fact. The zero-point energy of the vacuum is the minimum energy that a quantum system can possess. And it is always greater than zero. The Heisenberg uncertainty principle, one of the foundational pillars of quantum mechanics, guarantees this. You cannot simultaneously know the exact position and momentum of a particle with perfect precision. And by the same token, you cannot have a quantum field sitting perfectly still at zero energy. There will always be fluctuations. These fluctuations have real, measurable consequences. One of the most striking is the Casimir effect. First predicted by the Dutch physicist Hendrik Casimir in 1948 and experimentally confirmed with high precision by the American physicist Stephen Lamoureux at the University of Washington in 1997. The experiment is elegant in its simplicity. Place two uncharged metallic plates extremely close together in a vacuum, separated by a distance of less than a micrometer, and you will find that they are pushed toward each other by a tiny but measurable force. No electric charge, no magnetic field, no external push. The force arises purely from the quantum fluctuations of the vacuum between the plates. The plates restrict which fluctuations can exist in the gap between them. Only certain wavelengths can fit, while the fluctuations outside the plates face no such restriction. The imbalance creates a net inward pressure. It is as if the vacuum itself is gently squeezing the plates together. Lamoureux's 1997 experiment confirmed the theoretical prediction to within 5% accuracy, and subsequent experiments have refined the measurement further. The Casimir effect is not exotic fringe science. It is a well-established phenomenon that must be accounted for in the design of micro and nanoscale devices. It is engineering reality. Beyond the Casimir effect, the quantum vacuum is also the birthplace of virtual particles, fleeting pairs of particles and antiparticles that pop into existence and annihilate each other so quickly that they cannot be directly observed individually, but whose collective effects leave fingerprints all over physics. Virtual particles contribute to the Lamb shift, a tiny but measurable change in the energy levels of hydrogen atoms that was first observed by the American physicist Willis Lamb in 1947 and helped launch the development of quantum electrodynamics. They contribute to the anomalous magnetic moment of the electron, one of the most precisely measured quantities in all of science, matching theoretical predictions to better than 1 part in a billion. They are not figments of mathematical imagination. They are consequences of the quantum nature of fields, and their effects are as real as the device you are using to read these words. More recently, a team of researchers in Switzerland used advanced crystal optics and ultrafast laser pulses to directly detect the electromagnetic field fluctuations of the quantum vacuum, not their secondary effects, but the fluctuations themselves. This experiment pushed the boundary of what can be measured, confirming once again that what we call empty space is in fact a roiling sea of activity. So when a physicist talks about nothing in the context of the vacuum, they are not talking about the kind of nothing that a person on the street imagines. They are talking about a state with no particles, yes, but one that is saturated with energy, suffused with quantum fields and crackling with fluctuations. It is a profoundly active, dynamic state. It is the quietest the universe can be, and it is still not quiet. It is a canvas that is never blank. Now, knowing what the quantum vacuum actually is, let us revisit the claim that the universe came from nothing. Several of the most prominent physicists of the last half-century have used this phrase, and their arguments deserve careful examination, not because they are wrong about the physics, but because the word nothing is doing an enormous amount of work in their sentences. And not everyone realizes it. The late Stephen Hawking, perhaps the most famous physicist since Albert Einstein, spent much of his career thinking about the origin of the universe. Together with the American physicist James Hartle, Hawking developed what is known as the no-boundary proposal, published in 1983. The idea is breathtaking in its ambition. Hawking and Hartle proposed that the universe has no boundary in time, no edge, no starting point, no moment of creation. Instead, they argued, time itself behaves differently near the origin of the universe. As you trace the history of the cosmos backward toward the Big Bang, time gradually becomes indistinguishable from a spatial dimension. It does not hit a wall. It does not reach a sharp beginning. It smoothly rounds off, like the surface of a sphere approaching the North Pole. The North Pole is not the edge of the Earth. There is nothing north of it. But the surface of the Earth does not end there. It simply curves around. In the same way, Hawking argued, the beginning of the universe is not an edge of time, but rather a place where the geometry of space-time smoothly closes. And asking what happened before the Big Bang is like asking what is north of the North Pole. The question becomes meaningless because the very framework that gives the word before its meaning. Time does not extend beyond that point. In his best-selling 1988 book A Brief History of Time, Hawking wrote that because the law of gravity exists, the universe can and will create itself from nothing. This sentence electrified the public. It seemed to be saying that physics had finally explained the ultimate question, why there is something rather than nothing. But look at the sentence closely. Because the law of gravity exists. That is a precondition. Hawking is not saying that the universe emerged from absolute nothingness. He is saying that given the existence of physical laws, in particular the law of gravity, the emergence of a universe is inevitable. The word nothing, in Hawking's usage, means no matter, no radiation, no pre-existing stuff. It does not mean the absence of physical law. The law of gravity, and the quantum fields that accompany it, are already something. They are a framework, a structure, a set of rules. And for the no-boundary proposal to work, that framework must be in place. Hawking's nothing is not the philosopher's nothing. It is a physicist's nothing, a technical term that carries hidden cargo. The American theoretical physicist Lawrence Krauss pushed the universe from nothing idea even further in his 2012 book A Universe from Nothing. Why there is something rather than nothing. Krauss argued that quantum mechanics and general relativity, taken together, show that a universe can spontaneously pop into existence from a quantum vacuum without any need for a supernatural creator. His argument leaned heavily on the concept of the zero-energy universe. The idea that the total energy of the universe might be exactly zero, with the positive energy of matter and radiation perfectly balanced by the negative energy of gravity. If the cosmic books balance to zero, then no net energy needs to be borrowed for the universe to come into being. It is, in a sense, a free lunch. Krauss presented this idea with considerable flair, and it received enthusiastic endorsements from prominent atheists and skeptics, including the evolutionary biologist Richard Dawkins, who wrote the afterword to Krauss's book. But the argument also drew sharp criticism, most notably from the American philosopher of science David Albert, who teaches at Columbia University in New York. In a scathing review published in the New York Times in March 2012, Albert argued that Krauss was playing a shell game with the word nothing. The quantum vacuum that Krauss describes as nothing, Albert pointed out, is a particular configuration of relativistic quantum fields. It has structure. It obeys laws. It possesses energy. It is something. And the question that Krauss claims to have answered, why is there something rather than nothing, is actually the question of why those quantum fields exist at all. Krauss, Albert wrote, has not answered the question. He has merely pushed it back one step. Where did the quantum fields come from? Where did the laws that govern them come from? Why do those laws have the form they do? These are the real questions, and they remain as open and as mysterious as ever. Albert's critique was not pedantic nitpicking. It struck at a genuine and important distinction. When a philosopher or an ordinary person asks, why is there something rather than nothing, they typically mean something like, why does anything exist at all? Why is there a universe? Why is there anything? Krauss's answer effectively says, given the existence of quantum fields and the laws of physics, a universe can arise spontaneously. But that answer presupposes the existence of quantum fields and the laws of physics, which is precisely the kind of something the question was asking about. The physicist George Ellis, a longtime collaborator of Hawking and one of the world's leading cosmologists based in South Africa, made a similar point. Ellis noted that Krauss's argument does not explain why the laws of physics exist, why they have the specific form they do, or why quantum fields are a feature of reality. These are foundational questions that physics, at least in its current form, does not address. To be clear, neither Hawking nor Krauss was being dishonest. Both were describing real and important physics. The no-boundary proposal is a serious scientific hypothesis that has generated decades of productive research. The zero-energy universe concept is a legitimate idea in theoretical cosmology. The problem is not with the physics, but with the rhetoric. When these ideas are packaged for popular consumption, and the word nothing is splashed across book covers and documentary titles, the public understandably takes it at face value. They hear, the universe came from nothing, and they think it means what it sounds like it means. That there was once a state of absolute, total, unqualified emptiness. And then, poof, a universe appeared. That is not what the physics says. What the physics says is something more like, given a certain set of physical laws and quantum fields, a universe can emerge from a state with no particles and no classical spacetime. That is a remarkable and fascinating claim. But it is a very different claim from the universe came from nothing. The gap between those two statements is where most of the public confusion lives. This leads us to one of the deepest and most disorienting questions in all of cosmology. Can we even talk about what came before the Big Bang? Is the question itself coherent? The answer depends on what theory you are using. And the honest answer is that we do not yet know for certain. In standard general relativity, the theory of gravity that Einstein published in 1915, time and space are not fixed, pre-existing arenas in which events play out. They are dynamic, flexible, and intertwined into a four-dimensional fabric called spacetime. Spacetime can bend, stretch, warp, and even under extreme conditions, develop singularities, points where the curvature of spacetime becomes infinite and the equations of general relativity break down. When you trace the expansion of the universe backward in time using general relativity, the equations predict that the density and temperature of the universe increase without limit, eventually reaching a singularity, a point of infinite density, infinite temperature, and zero volume. This is the initial singularity, and in the classical version of Big Bang cosmology, it represents the boundary of time itself. There is no before the singularity because time begins there. It is not that we do not know what happened before. It is that, according to this framework, the word before has no meaning. Time simply does not extend beyond that point. But there is a massive caveat. We know that general relativity is incomplete. It is a classical theory, meaning it does not incorporate the principles of quantum mechanics. And at the extreme conditions of the initial singularity, temperatures above 10 to the 32nd power degrees, densities exceeding anything we can create in a laboratory, volumes smaller than a subatomic particle, quantum effects cannot be ignored. We need a theory that combines general relativity with quantum mechanics, a theory of quantum gravity, and we do not yet have one. What we do have is a boundary, a wall of ignorance, defined by what physicists call the Planck scale. The Planck time is approximately 5.39 times 10 to the negative 44th power seconds, an interval so inconceivably brief that it makes a femtosecond look like an eternity. The Planck length is about 1.6 times 10 to the negative 35th power meters, roughly 100 quintillion times smaller than a proton. At these scales, the smooth, continuous spacetime, described by general relativity, is expected to dissolve into something fundamentally different, a quantum foam, perhaps, or a network of discrete spacetime atoms, or something else entirely that we lack the mathematical tools to describe. The point is this. Our current physics can trace the history of the universe backward to within a Planck time of the initial singularity, but it cannot penetrate that final barrier. What lies at or beyond the Planck epoch is terra incognita. We have educated guesses, promising mathematical frameworks and tantalizing hints, but no confirmed theory and no direct observational access. The singularity predicted by classical general relativity is almost certainly not real. It is a signal that the theory has been pushed beyond its domain of validity, like trying to use Newtonian mechanics to describe objects moving near the speed of light. The singularity is not a feature of the universe. It is a feature of the limitations of our current best theory. What actually happens at the Planck scale, whether time has a beginning, whether it extends infinitely into the past, whether it transforms into something unrecognizable, remains one of the greatest open questions in all of science. So if we cannot look behind the Planck wall using standard physics, what do our best theoretical candidates say? This is where things get truly fascinating, because the leading proposals for what happened at or near the beginning of the universe do not converge on a single story. They point in wildly different, sometimes contradictory directions, and every single one of them complicates the naive picture of a universe popping out of nothing. The first and most influential of these proposals is inflation theory. In the late 1970s and early 1980s, physicists realized that the standard Big Bang model, while enormously successful, had some puzzling features that it could not explain on its own. The universe is extraordinarily uniform. The CMB temperature is the same in every direction to 1 part in 100. 000, even between regions of the sky that, in the standard model, would never have been in causal contact with each other. How did opposite sides of the sky agree on a temperature if light never had time to travel between them? This is the horizon problem. Additionally, the universe appears to be geometrically flat to extraordinary precision. In general relativity, the geometry of the universe depends on its energy density, and flatness is an unstable condition. Even a tiny deviation in the early universe would have been amplified over billions of years into a dramatically curved cosmos. But observations show the universe is flat to within about 0.5%. How did the universe end up so precisely balanced? This is the flatness problem. In 1981, the American physicist Alan Guth, then at the Stanford Linear Accelerator Center in California, proposed a radical solution to both problems at once. He suggested that in the first fraction of a second after the Big Bang, specifically during the interval between roughly 10 to the negative 36th power and 10 to the negative 32nd power seconds, the universe underwent a period of exponentially rapid expansion, inflating by a factor of at least 10 to the 26th power in a time span shorter than the blink of an eye. This inflationary phase would have taken a tiny, causally connected patch of space and stretched it to enormous size, smoothing out any irregularities and flattening the geometry, neatly solving both the horizon and flatness problems. The idea was refined and developed by physicists including Andre Linde at Stanford, Paul Steinhardt at Princeton, and Andreas Albrecht, and it quickly became a cornerstone of modern cosmology. But inflation introduced a new and deeply strange consequence: eternal inflation. In the 1980s, physicists including Linde and the Russian-American cosmologist Alexander Vilenkin at Tufts University in Massachusetts showed that once inflation starts, it may never fully stop. The energy field driving inflation, called the inflaton field, decays at different rates in different regions of space. In some regions, it decays quickly, ending inflation and allowing a normal, slowly expanding universe to form, a bubble universe like ours. But in the regions between the bubbles, inflation continues, stretching space at an exponential rate and spawning new bubbles endlessly. The result is a fractal landscape of bubble universes, each potentially with its own physical constants, its own particle physics, its own version of reality, all embedded in an eternally inflating background. This is the multiverse, not in the science fiction sense of parallel worlds accessible through a portal, but in the theoretical physics sense of an infinite ensemble of causally disconnected regions of spacetime, each one a universe unto itself, most of them forever beyond our observational reach. The multiverse is not a proven fact. It is a theoretical prediction that follows naturally from well-established inflationary physics. But it has no direct observational evidence, and some physicists argue that it may be inherently untestable. It sits in an uncomfortable gray zone between physics and metaphysics, but its implications for the question of cosmic origins are profound. If eternal inflation is correct, then our universe is not unique. It is one bubble in an infinite foam, and the foam itself may have no beginning and no end. The concept of the beginning of the universe becomes local rather than global. Our bubble had a beginning, but the multiverse as a whole might be eternal. The beginning, such as it was, loses its special status. It becomes an event, not the event. Inflation theory has been extraordinarily successful in its predictions. It explains the uniformity of the CMB, the flatness of space, and crucially, the tiny density fluctuations that seeded the formation of all cosmic structure. But it also has critics. One persistent concern is that inflation is too flexible. The inflaton field has adjustable parameters that can be tuned to match almost any observation, which means the theory is difficult to falsify. A theory that can explain anything arguably explains nothing. This concern motivated a team of researchers based in Spain and Italy, including Dr. Raúl Jiménez of ICREA and Dr. Daniele Bertacca, to propose a striking alternative in 2025. Published in Physical Review Research, their paper presents a model they call inflation without an inflaton. The idea is that the scalar perturbations we see imprinted on the CMB, the density fluctuations, that grew into galaxies, were not generated by a hypothetical inflaton field at all. Instead, they were produced by gravitational waves interacting with the quantum fluctuations of de Sitter space, a mathematical model of an exponentially expanding universe named after the Dutch mathematician Willem de Sitter, who collaborated with Einstein in the 1920s. In this framework, no exotic new field is required. Gravity and quantum mechanics alone are sufficient to seed the large-scale structure of the universe. Dr. Jiménez described the motivation plainly for decades. Physicists have tried to explain the early universe using models built on elements that have never been observed. What makes this new proposal compelling is its simplicity and its testability. It does not add speculative ingredients. It demonstrates that gravity and quantum mechanics may be enough. The model makes specific predictions about the spectrum and properties of gravitational waves in the early universe. Predictions that could potentially be confirmed or refuted by next-generation gravitational wave observatories. If verified, it would represent a significant simplification of our picture of cosmic origins, stripping away one of the key unknowns, the inflaton field, and replacing it with physics we already understand. But inflation, with or without an inflaton, is not the only game in town. An entirely different approach to the question of cosmic origins has been gaining momentum. One that eliminates the Big Bang singularity altogether, the bounce. The basic idea is simple and intuitive. Instead of the universe emerging from a singularity, a point of infinite density where the laws of physics collapse, the universe might have undergone a phase of contraction, reaching some maximum density, and then bouncing back into expansion, like a ball hitting the floor and rebounding. In this picture, the Big Bang was not a beginning but a transition, a moment when a previously contracting universe reversed course and started expanding. The idea is not new. Versions of oscillating or cyclic cosmologies have been proposed for decades. But a particularly compelling new version was published in 2025 by Professor Enrique Gastenaga of the Institute of Cosmology and Gravitation at the University of Portsmouth in England. In a paper published in Physical Review D, Gastenaga and his colleagues proposed what they call the black hole bounce universe. The premise is startling. Our entire observable universe may exist inside a black hole that formed in a larger parent universe. Here is how the scenario works. In the parent universe, a massive concentration of matter collapses under its own gravity, forming a black hole. In standard general relativity, such a collapse leads inexorably to a singularity, a point of infinite density at the center of the black hole, where spacetime curvature becomes infinite and the equations break down. But Gastenaga's team showed that quantum mechanics intervenes before the singularity can form. Specifically, the Pauli exclusion principle, the fundamental quantum rule that says no two identical fermions, such as electrons or quarks, can occupy the same quantum state, prevents the collapsing matter from being squeezed into a point of truly infinite density. The collapse halts at an extremely high but finite density, and then the matter rebounds, bouncing outward into a new phase of expansion. That expansion, according to the model, is our Big Bang. The team found an exact analytical solution, no approximations, no numerical fudges, showing that the collapsing matter reaches a maximum density and then transitions smoothly into an expanding universe. Remarkably, the bounce naturally produces two distinct phases of accelerated expansion. One at the very beginning, corresponding to what we call cosmic inflation, and one at late times, corresponding to what we observe as dark energy. In the standard cosmological model, inflation requires a hypothetical inflaton field, and dark energy requires a cosmological constant or some other mysterious component. In the black hole bounce model, both emerge naturally from the physics of the bounce itself, with no additional ingredients required. The model also makes a specific testable prediction. The universe should have a small but non-zero positive spatial curvature. Current measurements show the universe is very close to flat, but a slight positive curvature, meaning the universe curves back on itself like the surface of a sphere, just very gently, has not been ruled out. The European Space Agency's Euclid mission, launched in 2023 and currently surveying the large-scale structure of the universe, may be able to detect this curvature if it exists. If it does, it would be strong evidence in favor of the bounce scenario. The philosophical implications of this model are profound. If the universe is the interior of a black hole in a parent universe, then our Big Bang was not the birth of everything. It was a local event, a transition within a larger, pre-existing reality. The question, what came before the Big Bang, has a concrete answer: a collapsing cloud of matter in another universe. And that parent universe may itself have formed inside a black hole in a yet grander universe. And so on, potentially ad infinitum. The chain of causation does not terminate in nothingness. It extends backward into a potentially infinite regress of nested universes, each one giving birth to the next through gravitational collapse and quantum rebound. These cutting-edge theories, eternal inflation, inflation without an inflaton, the black hole bounce, share a common theme despite their differences. They all point away from the idea of an absolute, beginning from absolute nothing. They suggest instead that what we call the Big Bang was either a local event within a larger structure, or a transition within a longer history, or the latest iteration in an ongoing process. The word beginning loses its absolute character. It becomes relative, contextual, provisional. And the word nothing becomes, if anything, even more problematic. This is where we need to step back from the equations and the telescopes and consider the question from a different angle entirely, from the perspective of philosophy and human cognition. Because the problem with nothing is not just a problem of physics. It is a problem of thought itself. The question, why is there something rather than nothing, is arguably the oldest and deepest question in all of philosophy. The German philosopher Gottfried Wilhelm Leibniz posed it explicitly in 1714 in his work, The Principles of Nature and of Grace, based on reason, and it has haunted thinkers ever since. It seems like such a simple question. Nothing, intuitively, feels like the default state. If there were nothing, no universe, no matter, no energy, no space, no time, no laws, there would be nothing to explain. Nothing requires no cause, no mechanism, no justification. Something, on the other hand, seems to demand an explanation. Why this? Why anything? But here is the paradox. Can you actually conceive of absolute nothing? Try it. Close your eyes and imagine a state of total non-existence. No space. No time. No darkness, because darkness is something. It is the absence of light within a space that exists. No silence, because silence is something. It is the absence of sound within a time that flows. No emptiness, because emptiness implies a container with nothing in it. And a container is something. The moment you try to picture nothing, you inevitably picture something, a void, a blackness. A blankness, an absence. But a void is a spatial concept. Blackness is a visual concept. Blankness is a property. Absence is a relation. Every attempt to grasp nothing smuggles in something. Your mind, it seems, is constitutionally incapable of representing absolute nothingness. And this is not a failure of imagination. It is a structural feature of thought itself. Human cognition operates on representations. We think in terms of objects, relations, properties, spaces, and times. We can negate, we can say not this, not that, but every negation is parasitic on the thing it negates. Not red, only has meaning if red has meaning. Not here, only has meaning if here has meaning. Nothing, only has meaning against the background of something. It is a derived concept, not a primitive one. The philosopher Martin Heidegger, who placed the question of being at the center of his philosophical project, argued that nothingness is not simply the absence of beings, but something more fundamental and more elusive, something that can only be approached obliquely, through experiences like anxiety, in which the familiar world of things recedes and one confronts the sheer groundlessness of existence. Whether or not one finds Heidegger's approach illuminating, the basic point stands. Absolute nothing is not something the human mind can straightforwardly think. It is a limit case, an asymptote, a concept that dissolves the closer you approach it. This has direct implications for cosmology. When a physicist says the universe came from nothing, the listener's mind immediately constructs a picture, a dark void, an empty stage, and then something appearing on it. But that picture already contains something, the void, the stage, the spatial and temporal framework within which the appearance occurs. The listener has not imagined nothing at all. They have imagined a very sparse something. And the physicist, when pressed, will usually admit that their nothing also contains something, quantum fields, physical laws, a mathematical structure. The word nothing is doing double duty, meaning one thing in everyday language and something quite different in technical physics. And the slippage between these two meanings is the source of enormous confusion. So where does all of this leave us? If the universe did not come from nothing, not from the philosopher's nothing, and not even, strictly speaking, from the physicist's nothing, then what did it come from? The honest answer is, we do not know. But we can say some things about what the answer might look like. And we can identify the deep structural features that any adequate answer will need to address. One possibility is that the laws of physics are themselves fundamental, that they do not emerge from anything more basic, but are simply the bedrock of reality. In this view, the universe exists because the laws of physics are such that existence is inevitable. The zero-energy universe hypothesis gestures in this direction. If the positive energy of matter and radiation is exactly balanced by the negative energy of gravity, then the total energy of the universe is zero, and its existence costs nothing in the cosmic ledger. A universe can, in a sense, bootstrap itself into existence because its net energy balance is nil. But as we have seen, this explanation presupposes the existence of physical laws and quantum fields. Where did they come from? Why do they have the form they do? Why is there gravity at all? These questions remain unanswered. Another possibility is that reality is fundamentally mathematical, that the physical universe is one expression or instantiation of a mathematical structure that exists necessarily, the way the number 7 exists necessarily, independent of whether anyone is around to think about it. The MIT physicist Max Tegmark has championed this view in his mathematical universe hypothesis, which proposes that every mathematically consistent structure exists physically as a universe. If this is true, then the question, why does the universe exist, has a breathtakingly simple answer. Because it is mathematically possible, and all mathematical possibilities are realized. The universe exists for the same reason that the integers exist. It could not exist. This is a radical and highly speculative idea, and it raises its own set of questions, notably, why should mathematical existence imply physical existence? What does it mean for a mathematical structure to exist physically? But it represents one pole of the debate, the view that existence is necessary rather than contingent, that nothing is not a coherent alternative, and that the question, why is there something rather than nothing, is based on a false premise. Yet another possibility, as the bounce cosmologists suggest, is that the universe is part of an infinite chain of causes and effects, each universe giving rise to the next, with no ultimate beginning and no ultimate end. In this case, the question, what came before, always has an answer, another universe, another state, another phase, and the concept of an absolute origin never arises. The buck is never passed to nothing, because there is always something. Each of these possibilities has its strengths and its weaknesses, its advocates and its critics. None has been proven. None has been definitively ruled out. The question of why anything exists remains, as the American philosopher William James called it, the darkest question in all of philosophy. But what we can say with increasing confidence is what the answer is not. The answer is not that the universe sprang from absolute nothingness. Every theoretical framework that physicists have developed, the Big Bang model, inflation, the no-boundary proposal, the zero-energy universe, the multiverse, Bounce cosmology assumes the existence of something, physical laws, quantum fields, mathematical structures, prior states of matter and energy. None of them starts from a blank slate. None of them starts from true nothing. The phrase, "the universe came from nothing," is, at best, a dramatic simplification used to capture public attention, and at worst, a fundamental misrepresentation of what the science actually says. Let us also consider a remarkable feature of the universe that bears directly on this question: the fine-tuning of physical constants. The universe we inhabit appears to be exquisitely calibrated for the existence of complex structures, including stars, planets, chemistry, and life. The strength of gravity, the mass of the electron, the charge of the proton, the cosmological constant, the relative strengths of the four fundamental forces, if any of these differed by even a tiny fraction from their observed values, the universe as we know it could not exist. Stars would not form, or they would burn out too quickly, or atoms would be unstable, or chemistry would be impossible. The range of values compatible with a universe capable of producing observers like us is, by any standard, extraordinarily narrow. This is the fine-tuning problem, and it admits of several possible responses. One is the multiverse, if an infinite number of universes exist, each with different physical constants. Then it is no surprise that we find ourselves in one of the rare universes where the constants permit life. This is an application of the anthropic principle. We can only observe a universe that is compatible with our existence. Another response is that the constants are not contingent, but are determined by some deeper theory that we have not yet discovered, a theory of everything, that would show that the constants must take exactly the values they do, with no room for variation. A third response is frankly theological. The universe was designed. This is not a scientific answer, but it is one that many people find compelling. And it has a long intellectual pedigree stretching back through Aquinas, Leibniz, and beyond. The point, for our purposes, is that fine-tuning adds another layer of complexity to the question of origins. It is not enough to explain why the universe exists. One must also explain why it exists with these particular properties, why the dial settings are what they are. And this makes the naive story of nothing exploding into everything even less satisfying, because it provides no mechanism for selecting the specific physical constants that happen to permit complexity in life. So here is the conclusion, stated as plainly and directly as possible. The universe did not come from nothing. It came from something that physicists have often labeled nothing for convenience or for rhetorical effect, but which is always, upon inspection, rich with structure, law, and potential. The quantum vacuum is not empty. Physical laws are not nothing. A prior universe is not nothing. A mathematical structure is not nothing. Whatever the ultimate origin of the cosmos turns out to be, it will not be nothingness. It will be something. Something that our current physics is still struggling to fully describe. Something that may require a new theory of quantum gravity, a new understanding of the relationship between mathematics and physical reality, or perhaps a conceptual revolution as profound as the ones wrought by Copernicus, Newton, and Einstein. But it will be something. What we have been calling nothing all along was never truly nothing. It was the most fertile, most dynamic, most extraordinary something imaginable, a substrate of pure potential, vibrating with quantum energy, structured by mathematical law, pregnant with universes. The universe was not born from an absence. It was born from an abundance so fundamental that we mistake it for emptiness. The way a fish might mistake water for nothing, because it has never known anything else. The story of cosmic origins is not a story about something appearing where once there was nothing. It is a story about transformation, about one state of reality giving way to another, about potential becoming actual, about symmetry breaking and structure emerging and complexity building upon complexity in an unbroken chain that stretches from whatever came before the Planck epoch to the stars and galaxies and planets and people that populate the universe today. The beginning, if there was one, was not a moment of creation from void. It was a moment of transition from one kind of fullness to another. And we, looking backward through 13.8 billion years of cosmic history, squinting through our telescopes and scribbling our equations and arguing about the meaning of words, are still trying to figure out exactly what that fullness was. We may never fully succeed. The ultimate nature of reality may always recede before our inquiries, like a horizon that moves as fast as we do. But we can say this much with certainty: the old story, the simple story, the comforting story of a universe born from nothing, that story is not true. The real story is bigger, stranger, and more wonderful than that. The real story is that the universe was never nothing. It was always something. And the deepest mystery is not why there is something rather than nothing. The deepest mystery is what that something is.